everyone. Today we're going to go off of thermochemistry and we're going to go into a little bit of thermodynamics. So I did this chapter last year when we went remote. I have a lot of videos made for it. A couple other things with thermodynamics is it actually builds off of what we did in the last chapter. So hopefully some of the topics aren't too terribly new besides the first couple sections that kind of introduce a couple things. So let's go ahead and get started. It says, in this chapter, we're going to explore the connection between energy and the extent of a reaction. And that's called thermodynamics, which is an area of chemistry that deals with energy relationships. Specifically in this chapter, instead of looking at enthalpy and the first law of thermodynamics, we're going to look on the other side, entropy, and the second law of thermodynamics. And this provides an insight of why physical and chemical changes tend to favor one direction over the other. Why does a reaction happen a certain way? So let's go and look at our thermochemistry review from last chapter, some things to bring in. Last chapter, we covered the nature of energy, and we said energy can be possessed in two different ways, as kinetic energy, which is energy of motion, like riding a bike, or potential energy, which is stored energy due to a chemical composition or what something's made up of, or based on its position, is a ball on top of a hill ready to roll down. Now, energy can be measured as both heat and work. That brings into the term we learned last chapter, enthalpy. It equals the internal energy of the system plus the product of pressure and volume. So the first law of thermodynamics stated that energy is conserved. There are a couple other ways you could write this. Another way you could write this or say this is energy is neither created nor destroyed in any process. Usually energy is transformed. Transferred or transformed. So it can be transferred between the systems and the surroundings, or it can be transformed in one form of energy to another form of energy. So here we express it as delta E, which is the change in energy, equals Q, which is heat, and W, which is work. Now the first law of thermodynamics, which is delta E equals Q plus W. Delta E, we stated, is a change of internal energy. Now, that delta E can be positive, which means that it's endothermic. It has absorbed energy. Or it can be negative, which means that it has released energy. So Q stands for heat absorbed or released by a system, and then W stands for the work done. Now we're going to start our first section, which is all about spontaneous processes. So what is a spontaneous process? It is a process that's capable of proceeding in a given direction without needing to be driven by an outside source of energy. What that means is things happen on their own without any outside assistance. For example, if you put water in a freezer, it's going to turn to ice. You don't have to input any extra energy. Heat is always going to be transferred to the hand if you touch a hot object. It just occurs. If you drop an egg, it's going to break. If you release a gas, it's going to expand to fill a room. These processes happen very, very easily, and they're the most probable cause that's going to happen when these things occur. Non-spontaneous is just the reverse of spontaneous. So these are things that are not likely to happen unless you have to insert energy. For example, if you put ice in a freezer, it's not likely going to melt. So if it does melt, that's non-spontaneous. Heat's not going to go from your hand to a hot stove. A broken egg isn't going to magically reassemble, and condensing a gas or putting it in a small container makes you use energy in order to do that. So in general, processes that are spontaneous in one direction are actually non-spontaneous in the opposite, like we gave with the examples above. This allows us to follow that first law of thermodynamics. Energy is conserved in both directions. It's not created nor destroyed. So one doesn't need energy and the other one does. So here we have a picture of a person dropping an egg. Dropping it and it breaking is spontaneous, but it going the opposite way is not spontaneous. And usually if you see videos of that happening, you know that they just put it in reverse. Now let's talk a little bit more detail about spontaneous processes. Processes that are spontaneous at one temperature and pressure can actually be spontaneous at other temperatures and pressures. So spontaneity depends on temperature in some instances. For example, if you have, let's say, ice, if it is above 0 degrees Celsius, it's going to be spontaneous for ice to melt. However, if it's below 0 degrees Celsius, the reverse process for it to freeze is spontaneous. So here it can be spontaneous in one of those temperatures depending on what you're doing. At 0 degrees Celsius, though, both processes are considered to be at equilibrium because that is the freezing temperature of water. So it can be both freezing and melting. There is no preferred direction which way it's going to go until you get that little slight temperature change. Okay. So here, spontaneous in one direction and spontaneous in the other, depending on the temperature. So again, if it's greater than degrees Celsius, it's going to melt. If it's less than, it's going to freeze. So depending on temperature makes it spontaneous. The other thing you have to realize about spontaneous processes is that they can be both fast and slow. Sometimes these reactions are too slow to even observe, such as rusting. Rusting occurs at such a very slow rate. It happens over time. It happens on vehicles due to the salt buildup that we use in Illinois and just the weather that we have outside. Thermodynamics tells us the direction that the reaction is most likely going to go. Is it going to form the products or the reactants? It doesn't necessarily tell us how fast. Okay. So a couple things. Let's identify some spontaneous processes. Here it says predict whether each process is spontaneous as described, spontaneous in the reverse direction, or if it's in equilibrium. So part A, water at 40 degrees Celsius gets hotter when a piece of metal heated to 150 degrees Celsius is added. So you have to think to yourself, does that typically happen? We did a lab with this. It's our calorimetry lab. Whenever we added the hot metal, yes, temperature did go up. So this is spontaneous. So here, part B, water at room temperature decomposes into H2 and O2. Well, think about it. Does this typically happen? If you have a glass of water, does it just randomly change to H2 and O2? Nope. So this would be non-spontaneous or spontaneous in the reverse direction. Okay. Part C, benzene vapor at a pressure of 1 atm condenses to liquid benzene at 80.1 degrees Celsius. Normal boiling point of benzene is 80.1 degrees Celsius. So here it says condenses. You kind of have to know what that means. Condense, if something condenses, it's turning into a gas to a liquid. So gas to a liquid and liquid to a gas happens at the boiling point. So here, if it's exactly at the boiling point, this is said to be in equilibrium. It can turn to a gas or a liquid to a gas. Neither one is actually favorable. Okay. And part D, it says at 1 atm, pressure of CO2 sublimes at negative 78 degrees Celsius. Is this process spontaneous at negative 100 degrees Celsius at 1 atm? So here we kind of have to know what sublime means. So dry ice sublimes. So this is going to be from a solid straight to a gas. Okay. So it happens at negative 78 degrees Celsius. If we're going to a gas, it has to be a little bit warmer. So is it going to happen at negative 100? No. So this is going to be in the reverse or opposite direction. Because if I'm going to a gas, I want this to heat up. not get colder. Okay. So here are a couple criteria for spontaneity. Spontaneous processes can be endothermic or exothermic. Most often you're going to see them as exothermic, but there are a few exceptions. Melting and evaporating are going to be spontaneous. They happen, but they're endothermic. So, for example, melting is spontaneous and endothermic whenever you leave something out in the hot sun, or evaporating if it gets hot enough, sitting outside with the sun hitting down on it. Now, remember, melting is where you're going from a solid to a liquid. Evaporating is where you're going from a liquid to a gas. The other thing about spontaneity is state functions are properties that define a state and do not depend how we reach that state. We only care about what we started with and what we ended with, not the path how we got there. So temperature, internal energy, enthalpy are all state functions. Heat and work are not state functions. Their values actually depend on the specific path taken between the states. So we have to keep that in mind when we talk about spontaneity as well. Now we're going to jump to the second part of this. How does spontaneous and non-spontaneous relate to something known as reversible or irreversible processes? So we're going to go in and talk about those as well. A reversible process. A reversible process, the system changes in such a way that the systems and surroundings can be put back in their original states by exactly reversing the process. Exactly. That's the key word in this definition. So, for example, if something freezes, can you put it exactly back into the melting point with the exact same process? This means you're going to restore the systems to its original conditions without any change in the systems or surroundings. You don't put in any extra energy. You don't use any extra energy. Now, with reversible processes, reversible change produce the maximum amount of work that can be done by a system and its surroundings. And we had a scientist who actually proved that is not necessarily the case. Most oftentimes, we see things that are irreversible processes. Irreversible process is one that cannot simply be reversed to restore the system and its surroundings to their original state. And it's funny because even though the other one is going to give us more work, most things that we observe are going to be irreversible. Spontaneous processes are irreversible. Breaking an egg, gas expanding, water freezing when it's cold, or water melting when it's warm. All of these are irreversible. For example, heat is always going to flow from hot to cold objects. It's impossible for heat to flow in the opposite direction. So heat flow, when we talk about temperature differences, is an irreversible process. Just like everything in science, there's always that little exception. How can it be made reversible? In order to take an irreversible process and make it reversible, heat has to have an infinitesimally small difference in temperature. And I mean like 0.0000001 small of a difference. Very, very, very tiny. Infamously small is denoted by this little O with a little hook on the top. For example, if you increase the temperature of a system by an infinitesimally small amount, heat can flow from hotter to colder. Or if you decrease it, it can go the opposite way. So here we have an example of heat leaving the systems to the surroundings when you add a small change. Here it goes from the surroundings into the system if you lower it. So there's a small little addition we're going to make to the reversible process definition. It is reversible if the reverse direction, whenever there's an infinitesimal small change made to some property of the system, such as a change in temperature. However, for a process to be truly reversible, the amounts of heat must be infinitesimally small, and the heat transfer must occur so slowly that it's very hard to observe this. So no process that we can observe is truly reversible. That's why we say usually heat flow is an irreversible process, because what we observe is it being irreversible. We're going to finish this by talking about isothermal processes, which iso means the same. Thermal has to do with temperature. So these are processes where we have a constant temperature. An example of an isothermal process is the expansion of a gas at a constant temperature. If we increase the temperature of a gas, it's going to expand and fill the room. An ideal gas is confined to the right half of a cylinder. What I mean by that is we have a picture here. We have a gas right here filling this area. We're going to have a partition, and then here we have a vacuum. Now, a vacuum means no air is in it whatsoever. Here it says when the partition is removed, the gas is going to spontaneously fill the whole cylinder. So if we take that partition out, gas is going to fill this entire area. No work is done. So work done, 0. So no work is done by the system when the gas expands. So there was no work. However, if we want to reverse that process, like we want to use a piston to compress the gas back to where it was, the surroundings is going to have to do work in order to do that. So even though the path that restores the system requires a different value of work, you still restored the system, but it's not considered reversible because of the work difference. The fact that the same path can't restore the system shows the process is irreversible. Because here, when work is put here and pushed to push the gas back, we have done work now. They're not the same. So this is considered irreversible. And in fact, most things that are constant temperature isothermal processes are going to be irreversible. Okay. So because real processes, the ones we observe, can at best only approximate the infinitely slow change in reversible process, all real processes are irreversible, or basically all spontaneous ones are. So a non-spontaneous process can only occur if the surroundings do work on the system. And any spontaneous process is irreversible. Even if we can return the system to its original condition, the surroundings have changed because they have used some type of energy. So they have changed because they have used energy or done work. Okay. So that's the end of today's lesson. Let me know if you have any questions. I know this is a lot of new stuff, a lot of new words. Make sure that you're asking and keeping up with it, because if you don't ask me, I can't help you. So I hope you guys have a good day.